The script test has no real GUI to speak of. As with the other scripted operators in particle flow, its real power is actually within the script itself. It does have one GUI element, and that is a random seed value that you can, if you wish, be picked up within the script and used within it. Let's have a quick look at two example scripts that I've actually produced for this test. As we're at a fundamental level, I won't actually dwell on these too much, but we can have a look at these and you can get an idea of how they actually work. The first one is I've created a script test here, and I've called it script scale. That isn't what it would normally be called. It would normally be called script test, but I've actually renamed it to be representative of what it actually does. You can see, just use rename to do that. As I said in the GUI, you can see I've actually got this option here, uniqueness, and that's a spinner, and that can actually be used within the script. That value can be picked up in the script and used as a seed for a random value if you need to. Let's quickly have a look at the script before we actually see what it does. And this is a very, very simple script. All it does is it tests for the scale of each particle. When it reaches a certain size, it actually then passes it on to the next event. So this sets up the scale channel here to be used within this test. If you don't actually declare channels within a script, they won't actually be accessible by that script. It's a way for the actual scripting system to save on resources and memory usage and execution speed and so on. You only actually declare channels that are needed. On init pcon2, we don't actually do anything in that particular area, so it's blank. On proceed, we actually do something. We count the number of particles in the particle system at that point, and then we say for I in 1 to count do, and that basically says for I, which starts off with, let's say, 0, in 1, so we set a range which would be 1, so I becomes 1, to count do. The count is whatever it is, let's say it's 20, then count would equal 20. So it's saying for I equals 1 to 20, do this. And that sets up a loop, which will actually loop through the next section 20 times and apply what is in actually these brackets 20 times. It'll apply it to each particle, basically. Then we have pcont particle index equals I. That means that the current particle index equals the current loop number. So on first entering, we'll actually have a loop value of 1. So the index equals 1. Then we loop again, it'll be 2, and the index equals 2, and so forth. These are very, very common, these lines here in most scripts. They are very basic setup commands, and they basically get you ready to actually loop through all your particles and apply something to them. Now, what we do is we actually do a test within the test, and the test is if the particle scale, pcon particle scale is the particle scale, is greater than, this is what the symbol means here, 2.5, then do what's in these brackets here. If it's not, it'll just carry on and finish the script for that particular particle. Then it'll loop around, and it'll loop around and round and round and round until it's done all the particles in this loop. You can see inside these brackets, what we actually do is we take pcont particle test status, which is a flag to the test, and we say you're true. So that basically makes the test equal true. So when our particles reach a scale which is greater than 2.5, they equal true, and this is actually set up here. So let's have a look what happens when we actually apply our particles. They've all got a scale which you can see is increasing, and when that reaches 2.5, they're sent on to the next event, and things are done with them. And there you go. You can see it's actually forming a spherical shape, and that's just mainly because the particles are spraying out in a random manner. And when they all reach a fixed distance from the original source icon, they all reach a value of 2.5. So it's very uniform, and that's creating this sort of spherical pattern that you can see here. If I actually set this up to have a much wider divergence, there we go. If I make it even more, and then we scrub back again, because a lot of those particles are ghost particles, which are just, there we go. Okay, and you can see it is actually pretty much a sphere. Now, if we used a random value for that test, we could actually break up that sphere quite a bit. We could actually say if the scale is greater than this value, and then just use a random value, then you can actually break up that spherical appearance a little bit and actually have it look a little bit more random. So that's what the first script test does. Let's have a look what the second one does. And for that, we'll just scroll back to the beginning. We'll change the divergence back to being something a little bit more sedate, so it forms a cone still. And that's because this time we're actually going to test for a proximity to this teapot here. And that teapot could actually animate and move around, and the test will pick that up. So we'll turn off the first test, turn on the second test, and you can see I've renamed this to script proximity to teapot, which is pretty representative of what it does. Now in this case we've got use time turned on. It doesn't actually need that as far as I can see in the script. It's just a hangover from what I've actually adapted it for. We'd need position, that is actually needed, so we've turned on that. We've got the usual setup here, the number of particles, and then a loop setup, and then inside the loop we set up the usual index number, and what we say is we create a variable called tpos. This is just a container for a value, and we say that tpos is equal to the teapot's position, and we can only get the teapot's position by actually referring to the teapot itself, and it'll actually get the teapot position and read that into this tpos here. Then we say if the distance, and in brackets, between the particle position and tpos, so it actually, this command here, distance, will actually take two vectors, 3-point values, in other words x, y, z values, and it'll compare them, and it'll produce a single float value. It'll actually produce a single value like 28 or whatever, 22.3 as a distance between those 2 points. And we're saying if that distance is less than 30, then do this. So in other words, when the particles get less than 30 units away from the teapot, they go into the next event. You can see we set up the test to test true at that point. So if we play, and we've got a proper cone, yes we have, should find that the particles now, there we are, when they reach 30 units away from the teapot, you can see they actually get sent on to the next event, where they're actually frozen in space. So that's a very basic example of what you can do with the test script. Anything that you can test in here can be used as a test, and you can have a number of things. You could say if the distance to the teapot is less than 30 and the particle is more than 20 frames old, then the test would be true. You could say if the distance to the teapot was a random value and the particle is more than 20 frames old and it's using this material, then the test would be true. If it's not, then it would be sent on to maybe another test below, another scripted test where something else could be tested for. Now in each case, as you can see, you're only ever going to be testing for one value, so you would have to use multiple test values if you wanted to test particles for different criteria. But apart from that restriction, it's completely flexible and you can do whatever you want with it. So it's very, very cool. And like all the other scripted operators in particle flow, is definitely worth learning. Scripting in particle flow really opens it up, and you can use things like the script operator, the birth script, you can use the test script, and you can use all of these features to completely open up particle flow to do things that you just cannot do either with the core features or with third-party tools. For instance, the particle flow tools boxes by Orbaz, they're excellent. They allow you to do many things that you can't do with the core package, but even those will obviously reach certain situations where you've got a very specific need and you have to do a very, very specific thing, and for those you really need scripting. So we'll be covering those, we'll be covering scripting in future DVDs, but this just gives you a preview of the kind of power that you have with these operators, and it's something that I've said in the other DVDs is very, very important to learn scripting. Okay, let's go on to the next test, which is the send out test.